Simulations of the universe are playing a larger and larger role in our understanding of the cosmos. And especially with some of the new galaxies that are being seen by JWST that are larger and more fully formed than anything astronomers had been predicting. And like, what role do simulations play? How are they built? How do they work? So I'm pleased to be joined by Dr. Andrew Pontzen today. He is a professor from University College London, and he recently wrote a book about how cosmological simulations are run and built called Universe in a Box. And so it was like perfect timing. I've been looking around for somebody to talk about this very topic, and they reached out to me to see if I wanted to interview Andrew, and it was absolutely perfect. We had a great conversation about the history of simulations, what role they play in science, when you should trust them, when maybe you shouldn't trust them, and how they fit within the astronomer's toolkit, what the future technology might hold for simulations. And of course, we've got to talk about the simulation hypothesis. Are we living in a simulation? So enjoy this interview with Dr. Andrew Pontzen. So what's it like physically to be in one of the rooms that is running one of these giant cosmological simulations? Like how big are these machines physically?
Oh, they're giant, and they're very loud. I mean, I think that's the thing that I'm normally struck by. We don't spend a lot of time in the machine rooms because most of it we are connecting over the internet, to be honest.
Right, you're just SSHing into your cluster and getting to work.
Yeah. SSH and sometimes bit of port forwarding here and there to do some technical stuff.
Right.
We don't. But most of the time, I'm sat in front of a laptop. But if you actually go into the machine rooms, they're huge, and they are deafeningly loud. And because a lot of those fans. Yeah, all those fans, and it's not just the fans of the machines themselves, but the cooling that goes around that, and a large fraction of the power that goes in is going into cooling. They are mighty impressive machines.
Like if you were gonna, like, one of the larger, more powerful supercomputers in the world, is it like walking around a warehouse size? Is it like a tennis court size? Like if you just tried to kind of wrap your head around what a modern top 10 supercomputer looks like physically.
Yeah, I mean, when you're inside, it's a little hard to tell because it's more like being in a supermarket, actually. There's just like these, you're surrounded by aisles, and instead of bananas and cornflakes, you've got just racks and racks of computers. Yeah. So when you're inside, you don't necessarily notice the scale of it. Yeah, I mean, I guess tennis court is probably a good rule of thumb.
I mean, I think in the olden days, you had the Cray supercomputers. It was this one fantastically quick machine, which now is maybe not as fast as what you hold in your pocket. But now with all of these computer farms that are out there, you might be walking along and someone could say, well, here's where the supercomputer starts. And here's where the supercomputer ends. But then the rest of this stuff over here, this is other computers, and this is all virtualization. And we think your supercomputer is kind of over there somewhere.
Yeah, that's right. I mean, I think if you're talking about a really large supercomputer, then you can identify all of the bits and pieces. But another thing we do quite often is run relatively small simulations. So it's not like every simulation is using giant fractions of huge supercomputers. Some of the simulations are running on maybe a few hundred CPUs. So you can fit that in just a few boxes. And so in that case, you probably have no idea where it's running. And it's entirely possible to do this in the cloud if you want to.
Right. Yeah. I know with a lot of modern machine learning work, you can go and purchase it by the hour. You can spin up in parallel as many processors as you can afford and run some of your machine learning. But I think like just the underlying architecture for the most powerful computers, that's a special bespoke setup that's more about how fast are these computers able to communicate with each other and all of the underlying data that's going back and forth, right?
Yeah, that's absolutely right. And this is especially true in astrophysics and cosmology applications, because one of the things that's quite special in our case is that every part of our virtual universes has some effect on every other part of our virtual universes. So if you imagine that, part of your virtual universe is inside this box and part of your universe is inside this box, they need to be able to talk to each other really fast. And actually, we really struggle with this. One of the real technical challenges is not ending up just constantly waiting for the communication. Even on these machines with super fast communication layers, like they have InfiniBand and things like this, even then, you can just end up completely blocked by communication if you're not really careful.
That's interesting. That the bandwidth to and from the processors gets to the point that it's the bottleneck over just the processing itself.
Yeah, that's exactly right. And it's not just necessarily bandwidth, but also latency as well that can be a big issue. And if you want to peer into the future or the near future, where everybody wants to be using GPUs, right? Because GPUs, in terms of their raw compute power, are incredibly impressive and so much more power efficient. But then this communication challenge gets even worse, because you can do all the internal number crunching so fast, but then you're just still going to be sitting around waiting for the communication with some far distant box in your supercomputer. So the technical challenges of running a simulation of the universe are something to behold.
Right. Just makes the simulation argument just that more infeasible. All right, so let's talk about the history of simulations. When did computers start to play a role in helping astronomers understand the cosmos?
I mean, pretty much as soon as they were invented, and arguably even before they were invented, in an ironic sense, that you can find examples of people who did what we would think of today as essentially simulations, but they did them without the aid of digital computers. So, there's examples like people who made scale models of galaxies out of light bulbs. And instead of trying to compute the gravitational forces between the different bits of the galaxies as we would on a computer today, they used the strength of light coming from the different bits of the galaxy as a kind of proxy for gravity. And in that way, they were able to do a kind of a by hand simulation and start to learn about how galaxies behave in what is essentially like a simulation, but it's just done by hand. So that was before digital computers came along. As soon as computers were available, astrophysics was one of the first applications. I mean, they became available around the end of World War II. They were first used for military applications, and of course, one of the famous first applications for computers was simulating the detonation of a nuclear blast, and in particular in the development of the H-bomb. And very quickly, people working on that realized, we can use this tool to understand supernovae in space. And because the explosion of a supernovae is extremely similar to a kind of scaled up mega version of an H-bomb. And not only that, but they realized they had to do it. There's a fantastic story in this book about somebody called Sterling Colgate, who was working on the H-bomb and realized that when you sign a nuclear test ban treaty, you have to know if you receive some gamma rays into some detector that you have in space, it could mean that the Russians have tested some prohibited device, and that you should this would precipitate a major political and world problem. Or it could be that you're actually looking at gamma rays coming from space, a much bigger explosion, but in some sense a kind of a similar one, much bigger, much further away, and completely harmless to humanity. And you better know which one you're looking at, right?
Right.
Because otherwise you you don't want to know what happens next.
Are we starting a world war or an interstellar war? We got to decide.
Exactly.
Yeah.
So, very early on, these computers were being used to do simulations of astrophysics. And then quickly, this carried on into simulating bigger and bigger things, simulating galaxies, and ultimately simulating the whole universe.
And I guess let's move towards that idea of simulating the whole universe, because what does that mean? I mean, the universe is big and the universe is old and there's a lot of moving parts. So how do simulations of the universe, how are they broken down?
Yeah, so we have a bunch of tricks that we use. And I think this is essential to understanding what a simulation is, that it is not a literal recreation of the universe. Right? So if we could literally recreate the universe, how big a computer would we need to do that? Well, in fact, you can prove you would need basically all the resources of the whole universe to build the computer that simulates the universe, right? So it's a physical impossibility to perfectly simulate the universe. So what do we do? Well, we do a bunch of tricks, and there's kind of two tricks. One is to make the universe that you're simulating small, so that it's, still very large compared to our everyday experiences, but small compared to the universe as a whole, so that maybe it's only, a billion light years across instead of 40 billion light years across. So that's one way you can kind of cut down the scale. But the other way that we cut down the scale of what's needed is to simplify. And the kind of simplification that I'm talking about is, imagine even just our Milky Way galaxy. It has hundreds of billions of stars. Even if that was the only thing you were simulating, that's already very challenging. And so what you end up doing is saying, well, we're not going to track every single star. We're going to track a handful of stars. And this depends on exactly what your goal is. But, it might be even just 1 million stars or something, or even fewer than that. And we're going to use that handful of stars as a kind of representative of the much bigger population. It's a bit like political polling almost. Like we're saying this is not everything there is, but it's a representative sample of what there is. So it gives us some idea of what's going on. And then you have to layer on top of that a bunch of extra assumptions about what are those stars going to do to the rest of the galaxy. And so it kind of comes in layers. There's physics at the bottom of it, but there are a lot of layers that we're adding on top in order to be able to get to something that is vaguely useful.
You don't need to simulate what I had for breakfast to calculate the movement of the Earth around the sun. And
right.
And that would increase the complexity, but it wouldn't necessarily provide a better simulation. So how do you decide what is meaningful enough to need to be simulated and will affect the outcome, and what is, not necessary and would just add noise?
Well, you've totally hit the nail on the head that is the hardest question. And that's the thing that tortures simulators. And to take your example of what you had for breakfast, you wouldn't think it would matter. And it's not going to matter to the Earth's orbit in the near term. But think about this: it is possible for small things to have a big effect in the long term. So, Lorentz was famous for pointing this out in relation to Earth's atmosphere. One of the things I'm talking about in the book is weather forecasting, because it has a lot of similarities to simulating the whole universe. And the concern there is that, as Lorentz put it, a butterfly flapping its wings in London today might ultimately give rise to a hurricane that's going to hit New York in a few weeks' time, because it's the tiniest effect can kind of lead to a sort of domino-like progression that changes the future in really surprising ways. So this is an effect known as chaos. It's something that is present in simulations. We can actually measure the presence of this by changing a tiny little thing in our simulation and restarting it and seeing that over time, things really do change. It really changes everything if you wait for long enough. Now, how long is long enough? I mean, in the case of your breakfast in the Earth's orbit, it would be many, many, many billion years, far longer than the lifetime of the sun, possibly longer than the lifetime of the universe, who knows, before it would really have a tangible effect on the Earth's orbit. But exactly as you're asking, we have to try and identify, therefore, which things matter and which things don't. And if you're interested in the way that galaxies form, for example, one of the most important things is how exactly do stars form? And when they live out their lives, what energy do they put back into the galaxy that they've arisen from? Because that energy then changes the galaxy that the stars are living in. There's the presence of energy heats up gas, and actually hot gas finds it quite hard to form into new stars. To form new stars, the gas has to get quite cool just so that it can kind of collapse under gravity and get dense enough to then start nuclear fusion. So there's this kind of interplay between the stars that are already there, the lifetime that the lives that they're leading and the energy that they're putting in on the one hand, and the new stars that are going to be born on the other. And that's before we even get onto black holes. And black holes also, despite being black, they're surrounded by these accretion disks where they're sucking in material, they're making the material hot, and that's generating energy that also goes out into the galaxies. So these are the kind of things, especially stars and black holes, we know they matter. And worse than that, we know we'll never model them perfectly. So there's this tightrope that we end up walking between, on the one hand, kind of despairing and going, everything matters. And so this is never going to work, which at points in my career, I have felt like that. But on the other hand, the other side of this tightrope is, hey, look, I just simulated the universe and here's what the universe looks like. And this is, and that's wrong as well. And so both of those things are wrong. That there is a line down the middle where you're kind of realistic about the limitations of what you're doing and flagging up that we've put in this bunch of assumptions and therefore there are these uncertainties. But it's a hard line to find, and that's what kind of keeps simulators awake at night.
Yeah. Well, I'm back to your, you were talking about weather forecasting, and I can remember being a child and seeing a weather forecast on the news and going, well, that's nonsense. I mean, who's going to, maybe tomorrow it'll be fine. But we're at the point now where I'll look at my long-term weather forecast in my weather app, see what it's going to be like in 10 days from now and go, okay, yeah, no, I that roughly, like, those 10-day forecasts roughly match my expectation for what the weather's going to be like. And I think most people say, oh, you can't trust the weather, man. But you kind of can now. And it feels like there must be some process that's gone on over and over again where people are just like, what if we had butterfly flaps? What if we had Fraser's breakfast? Wait, it's all starting to work now. What's that? What is that process?
Yeah, so you're exactly right. That is exactly the process that's going on. I mean, I think there's a couple of reasons why the weather forecast has improved so much over the last 15, 20 years. Or maybe even three reasons. I mean, one is that the resolution is increasing. So that's just the raw power of the computer, the fact that you can divide up the atmosphere into smaller and smaller pixels, if you like. And if you're tracing things in that way in kind of more and more detail, the more detail you can put in now, the better your ability to predict what's going to happen in 10 days' time. So that's part of it. Second part of it is our ability to monitor the atmosphere, actually. So just weather stations, weather satellites, the fact that these are being that these are really keeping on top of the conditions right now in the atmosphere, so that the predictions for 10 days' time, again, they're just more accurate because of that. But yeah, the third thing is exactly what you mentioned. It's what we refer to as the subgrid, actually. So it's the collection of things where we can't write down from first physical principles what's going to happen. A great example would be storm clouds. So storm clouds are really hard to predict and model because they come from thermals, basically in the atmosphere where hot air starts rising. It can be in quite a small area. It can be a mile or less across, and this hot, damp air starts rising. It shoots up into the upper atmosphere. When it gets there, it cools down and it generates the storm cloud. Now, it's incredibly hard to predict exactly where that's going to happen because it relates to tiny initial instabilities in the atmosphere that then kind of cascade. And so that's where this idea of a subgrid model comes in, that we're basically going to say, we don't know really how this works. We don't have enough resolution to be able to see it happening anyway. So we're just going to say, we're going to add some very approximate rules about if it's this hot, if the surface conditions are like this, and the overall wind pattern is like this, then clouds are going to form. And we're going to just put in a bunch of unknown parameters that basically are knobs that you can twiddle. And those knobs just adjust when it forms clouds versus when it doesn't. And if you're a weather forecaster, in a way, that's your entire career is based on twiddling those knobs and doing better and better. And it doesn't necessarily matter why the knobs take a particular value. All that matters is that you get better at predicting the weather. And there's loads of data to calibrate your models on. And in fact, machine learning is starting to come into this because you can use machine learning to do the knob twiddling for you, to just learn what are the conditions under which clouds form without worrying about all of those details that you can't really capture. So for weather forecasters, that's the name of the game. And something parallel is going on in cosmology when it comes to galaxies, when it comes to the effects of these stars and black holes and so on.
Well, I want to talk about this sort of fairly recent, I don't know if controversy is the right word exactly, but with JWST launching, you've got this telescope that's able to peer into a time in the universe that astronomers had not been able to get access to before. We're seeing galaxies as they looked just a couple 100 million years after the Big Bang. And they're finding galaxies that are surprisingly large, according to some models, which are demonstrated through these gigantic computer simulations. But then other computer simulations say, no, this is perfectly fine. In fact, expect even larger ones. And it all still fits within the Lambda CMD model of cosmology. So how is, the rubber is hitting the road now? And are we sort of like, so sort of give me a sense of like how this compares to the weather forecasting?
Yeah, I mean, we're at an incredibly exciting and interesting time with these results from JWST. They're definitely provocative, let's say that. And I think that, the teams that are producing these are doing an incredible job. And the JWST itself is just the quality of what's coming from that. It's beyond everybody's wildest dreams. And people had high hopes, but they've definitely been exceeded. So I think it's incredibly exciting. The main thing I would say, though, it's very early days. We're 1 year into this, right? JWST has been taking data for 1 year. That means there's a huge amount of uncertainty in how to interpret what we're seeing. So I can take a parallel example, actually. When the Hubble Space Telescope launched, so this would have been early to mid-90s, it went through a similar exercise. I mean, it started staring at patches of the sky and cataloging what the galaxies are out there. And what it found did not match any individual person's or computer model's expectations. It really didn't. And there was a kind of crisis of confidence in the field. It's so interesting going back now and reading that. I mean, I was at school at the time, so I wasn't playing any part in this, but going back and reading all this, it's so interesting to see the kind of the kind of motions that people went through, and it was accompanied by a sense of, wow, we got everything wrong. The galaxies are not what we expected. What the is going on here? However, what then happened is that people went, well, hang on a second. We hadn't got quite right this stuff that we were talking about already, about how the stars and the black holes actually affect the galaxy that's being built. And so then the simulations were revised, and they started to come into agreement with observations like the Hubble Deep Field. Now, I know what you're thinking. You're thinking, well, that's not science, right? Because that's just kind of fiddling the results to kind of match what you saw after the fact. And I think that's a fair criticism, and it's a criticism that was kind of leveled at this whole process at the time. But the thing is, having done
it's not what I'm thinking. Like
it's not what you're thinking.
I know too much. So, but right, because in my opinion, this is how you reject hypotheses. So this is the process of hypotheses rejection, and whatever remains is giving you an inkling of what is the right direction. But please continue.
Yeah. No, okay. So I shouldn't have said that's what you're thinking, but it's what a lot of people did think at the time. And I think what a lot of people continue to think today. This is 100%. Something that gets leveled in simulation.
Yeah, I see this comment all the time on my YouTube videos. Someone swoops in and just and makes that accusation. Right.
And I think it's worth talking about it head on, because honestly, it is a difficult thing. And I think as astronomers, it's right to just talk about this openly, that we do have to go and twiddle our models to make them fit reality sometimes. I think the distinction between the weather and the cosmology, with the weather, you always have the future to test out your model, that you can say, okay, we've twiddled all of our settings. Now let's run the world into the future and see what happens. And suddenly, our models were more accurate. Therefore, we're getting a better sense of what is right and wrong. But we can't watch the cosmos unfold in real time in a way. All you have is attempting to fit your data against history. That's exactly right. Yeah. And so, I mean, you can go two places with that. One is to use new observations. So you can make predictions for new observations and then test them against something that's never been seen before. So a great example of that recently would be the discovery of gravitational waves, say, which is also, a lot of simulations involved in that as well. And another thing that's coming up is measures of the cosmic web, where we kind of map out the galaxies across the universe and so on. That's another thing where you can actually put things directly to the test with new observations. So that's one thing you can do. So it's not like you're getting new data about how the universe is evolving, because it's evolving too slowly for that. But you are getting new data that you never knew before about what's already out there in the universe. So that's one way we can put things to the test.
That's interesting. And so it's like
work.
Right. But I'm sort of imagining, like, if you are an archaeologist and you think you understand a culture's road structure or logistics, then you could say, based on what I've learned so far, I predict that you will find an ancient city over there, and you pick a spot on the map that nobody has explored, and then they dig and they find the city. Could be luck. Yeah. Could be that you do understand. And so same thing, archaeology is just history. There's no way to go forward in time with archaeology, but you can still make predictions and make observations that give you a better sense of whether or not you're right.
Yeah, I think that's a really great analogy. And so there are things that we can do. And there are cases where we've actually been able to simulate and predict things in advance that have turned out to be spectacularly right. So sometimes we get things absolutely spectacularly right. And other times things come out wrong. But if you look at something like JWST or indeed the Hubble example I was giving a moment ago, the things that are coming out wrong, they're not they're within the kind of realm of things that we didn't really expect to be exactly right. Then they are not so far off that I personally would panic about them at this stage. They don't threaten the overall model. It is a challenge. We have to figure out, well, in what specific way were we wrong about this? Because we were, I think, overall slightly wrong about this. But it's not so far off the charts of what we were expecting to see that it would justify some of the more sensational headlines that have come out of this.
Right. Big Bang wrong.
Big Bang wrong would be a totally wrong conclusion to draw from this. There is so much data that shows about the expanding universe, including, light that's far older than the light that the James Webb Space Telescope is picking up right now. So it comes back to that tightrope, right? I mean, you're constantly walking this, that you don't want to say, well, it's all fine, because there's definitely some challenges there that we have to face. But equally, to say that this is a giant problem with cosmology is also wrong. There's a middle line there, and that's the one that we're walking right now.
Mm-hmm, mm-hmm. So let's talk about some of these larger simulations. Like what are they simulating? And I guess that obviously they're simulating different aspects of the same problem, but give me an example of a simulation and what it is trying to simulate.
Okay, so I mean, you could take something like the illustrious TNG simulations. You can go and get beautiful images of these. And the goal there is really to understand how galaxies form. But if you want to understand that, then the place you have to start from is the fact that there's a huge variety of galaxies out there. And so it's no good we're talking earlier on about, do you simulate the whole universe? Well, that's no good, because you're never going to be able to say anything about the individual galaxies. Your computer's not going to be powerful enough. But equally, if you sort of choose a tiny box, which only has one or two galaxies in it, then you're zooming in too far. You're not going to understand really anything from that. You have to choose some sort of middle ground. And so in this case, their simulations are a few 100 million light years across. That's the kind of scale that we're talking about. That's enough to have a very large number of galaxies, and perhaps even more importantly, to see those galaxies in lots of different environments. We talk about environments in the universe, meaning that some parts of the universe are just more dense, they have more stuff going on. Other parts are more like a void, and you just have one galaxy there if you're lucky. And if you really want to understand galaxy formation, you need to see things going across all of these environments. And so that would be a project like that, is kind of trying to, on the one hand, have enough detail in the galaxies to say something meaningful about them. On the other hand, have enough volume that you've got enough galaxies that you get a kind of statistical sense of which galaxies are more likely and less likely. So that's one example, but it's by no means the only way you can balance this. You can go to there are two extremes there. But the extreme that you can go to, where you actually try to simulate a significant volume of the universe, where now you're, tens of billions of light years across. You're not going to get any detail in the galaxies at this point, but it can be important for understanding the formation of the cosmic web, for understanding what we expect to see with forthcoming telescopes like, Vera Rubin Observatory in Euclid and things like this. So that's the other extreme. And then down at the sort of very mini scale, you can, if you want to, just go ahead and simulate the formation of a single galaxy. And then you have to be really careful about how you're interpreting that, because that's just one galaxy, and you can't necessarily map that onto any particular galaxy in our universe.
And galaxies don't form alone. I mean, you've got the influence of the other galaxies around them, whether or not perhaps they've got a quasar that's aimed right at the galaxy that is suppressing star formation. There was, back to that, the thing you talked about earlier about stars and the gas that's around them. There was a paper that just came out just a couple of days ago about star formation in the Tarantula Nebula, with observations done by the Sophia telescope, and they were able to map out these regions where you shouldn't get star formation, and yet there is star formation. And it turns out it's the magnetic fields that are helping to channel the gas into regions to change the pressure so that you get a more orderly star formation than you were expecting. Do you get these situations where you're like, oh, we didn't think about magnetic fields, and when we add magnetic fields, everything is different?
Yeah, absolutely. I mean, so you're absolutely right. First of all, you can't see a single galaxy in isolation. So even when you're doing one galaxy, you also need to include the stuff around it. Otherwise, what you're doing is essentially meaningless. So you've got that pulling you in one direction. Yeah, and the other direction, you have all of these effects. And it's almost like a joke at astronomy conferences, right? Where you present your beautiful work that you've done, and somebody in the front row raises their hand and they say, what about magnetic fields? And you know, it's the joke because nobody knows how to do magnetic fields in their simulations. I mean, people try, but it's incredibly challenging to get that right. And then even if you get the magnetic fields right, then there's things like cosmic rays. They probably also have a huge role to play in setting all of these things and how fast the new stars form and so on. So, I mean, this is like it's an endless enterprise, right? You could go on forever adding all of these things, and the question becomes like, well, what are we really trying to do? And I think the answer to should I put magnetic fields in my simulation depends on what question am I trying to answer. And I think, you know, the really groundbreaking work in this whole field always comes about because it has a clear question. It's not going, oh, I'm going to recreate the universe. It's more saying, I want to understand X, Y, and Z, whatever that is. Is it the cosmic web, or is it the role of magnetic fields in changing the interstellar gas? Whatever it might be, if it starts from a clear question, that then tells you, where am I going to focus my effort?
So back to this issue of, you know, these two big galaxies too soon. You know, based on what you saw the astronomers go through in the Hubble launch era, how do you think this whole thing will play out in the JWST era? Well, what will, you know, when we're 30 years on, what will have happened?
Well, I very much hope in 30 years that we will have a much better understanding of how galaxies form, and in particular, how they form early in the universe and how that ties in with the formation of their black holes. So I think, you know, one of the things that we really are only just starting to scratch the surface of is the very deep relationship between galaxies and their central supermassive black holes. And, you know, these have we know they have a profound effect on galaxies, but we don't really understand that effect in detail. And we don't really understand, slightly embarrassingly, where those supermassive black holes came from exactly. I mean, there are ideas, but it's wide open at the moment. So I think, you know, from the data side, when you take something like JWST, and then you imagine yourself in a future where we're also going to have things like LISA, which is the gravitational wave detector in space, that is going to be able to do something a bit like JWST in the sense it's going to look all the way back to the formation of the very earliest objects, and tell us about gravitational waves coming from them and therefore the black holes in them. I think it's going to be that kind of collaboration of the data between those kinds of facilities alongside our ability to model things better that is really going to change our picture of how this worked in the early universe.
And add in the neutrino detectors.
Oh, yeah. I mean,
add in the neutrino
also
detectors,
Yeah, absolutely. I mean, I think, you know, more broadly, what we call this is multi-messenger, right? That we're not going to rely any longer on just optical or infrared telescopes. We want to take everything together. It gives you a much richer view of what's going on.
And do you think that we will get to the point that we're roughly understanding the evolution of the universe from some point close to the Big Bang till today?
I mean, I think yes and no, in the sense that I think that the questions we have now, and to take a specific one, like why are these galaxies so large and bright, being one, I think, you can see those being answered. Those are the kind of questions you can answer. On the other hand, I think the history of science teaches you every time we answer one set of questions, it creates another set of questions. So, to take an example from the history of simulations, where does the structure in the universe come from in the first place? Well, that's kind of been answered now by the idea of dark matter, coupled to some ideas about the early universe and coupled to the power of simulations to trace that all through. But it's replaced by the question, well, what is dark matter then? I mean, who ordered that? Where did that come from? And so we tend to, we answer questions, but we also replace them with new questions. And I think, although we don't know what the new questions will be, we can see that some answers will come. I don't think it will herald the end of cosmology. I don't think we'll then go, hey, you know what? We understand it now. That's that. I think instead it will result in a new and equally exciting set of questions.
Right. So where is the technology going? I mean, obviously we are getting larger and larger, always getting larger and larger and faster computers. There are these new GPUs coming out of NVIDIA that are like $10,000 a piece and have ludicrous capability on board. We talked about the bandwidth issues of communicating between these things. There's potentially quantum computers coming out. What is the larger trend in simulations at this point?
I mean, right now, the thing that people are tearing their hair out over is how to make good use of GPUs. They are incredibly, incredibly hard for astrophysics problems. But we know that we have to use them. That's just the way that you're going to be able to get more calculations. And we know that if you want to understand things better, you need more resolution, more volume, and therefore more calculations. So I think, in the kind of medium term, by which I mean sort of 5-year type timescale, it's coming to grips with those kind of technologies that is going to drive the field on the technology and engineering side. If you look further ahead than that, then yeah, maybe quantum computers will start to have a role to play. Right now, we are a very long way from having the kind of quantum computer that could help us in cosmology, because they're noisy, they don't have a large number of qubits. So, what you would really want for cosmology is very high capacity, and you would want it to be as close to noise-free as possible, ideally fully error-corrected, and so, fault-tolerant quantum computing. I think, if you go and talk to experts in the quantum computing domain about this, my impression is that the best experts will not commit to a timeline for that. There's still a lot of technological challenges.
Yeah, in my understanding on the quantum computer front is they're mostly sure these things are actually quantum computers. That's where they stand right now in the capability of these devices, is that they're pretty sure they work, but not that they've mastered actually getting them to do work yet, just that they actually function as quantum computers. There's been a couple of, quantum supremacy tests. So it's very early on.
Yeah, that's my understanding too. And I think, the key for us is that noise level. So you can do very useful quantum computation on noisy quantum computers, which is what we generally have right now. And you can certainly do useful things, and you can certainly apply it in all sorts of fields. But I think for cosmology, we want to get to that noise-free level before it's obvious what we could use them for.
Yeah. Now, I know that in your book, you approach this idea of the simulation argument. And as a person who creates gigantic simulations, we've got to assume that if you ask the galaxies in your simulation, are you living in a simulation? The answer for them would be yes. Um, do you think that we are leading towards greater and greater simulations, that at some point we may get to a place where we are simulating entire worlds, civilizations, beings?
So I think it's very unlikely, in my view, that we are headed towards a future where we have simulations that at all recreate the experience that we have as humans. We live in this incredibly rich, detailed world. And more than that, we're able to build scientific instruments that probe it and show, at least as far as we can tell, that incredible rich detail extends across the entirety of space and time. So you're talking about, if you actually wanted to recreate that in a computer, then you would need demonstrably a computer that leverages all the resources of the universe in order to recreate a single universe. So you can actually show that. So we're not headed towards that, right? We're not going to take over the universe in order to run simulations of the universe. I mean, even if we could, that would just be stupid. So we're not going for that. Is there a possibility that we're headed towards some kind of simulations where from the inside it's possible to be a conscious being? I mean, maybe. I think it's clear, with the very fast developments in AI, it's clear that some kind of artificial general intelligence probably will come sooner or later. And maybe you could imagine having something where that even evolves within a kind of simulated world. So I don't rule out any of that. However, what I think it seems very unlikely is that we would want to run simulations which kind of trick the inhabitants of the simulations into thinking that they're in this kind of rich, detailed reality that we're in. I think it's much more likely, if you're going to do that, it would be in some much more kind of limited setting that you would be interested in doing that. Of course, there's all kind of ethical questions. If you really start to get things you really think you're creating conscious AI within these simulations. So there's a lot of questions, but I think fundamentally, the fact that you can't recreate the whole universe, that's just a law. And the fact that that then forces you to imagine that we're somehow being tricked. If you start imagining that we are somehow inside a simulation, then it's all a big trick. That leads you down a very specific path, and basically a conspiracy theory path. Very uncomfortable path. And I just don't think there's a motivation for us to make those simulations.
But isn't that sort of based on the assumption that base reality is in any way reflected in what's in the simulation? That
Correct.
Base reality could be vastly more complicated than the universe that we live in. It feels complicated, and if we were to think about how we would simulate this universe, we would need a simulation the size of the universe. But to simulate a simpler version that the inhabitants of that simulation would believe that they're, in reality, you could cut a lot of corners. And that you wonder, are we living in a universe that has a lot of corners cut?
Right. So first of all, there's no evidence for cutting corners that we can see. But fundamentally, you're right. You could imagine that there's a base reality which has just so phenomenally richer in terms of its physical resources that simulating our reality is just like a footling thing that it's or even if it's a supercomputer, it's just, you could imagine that. It's a logical possibility. I agree. However, what I always think about that possibility is that you are then presupposing a higher reality that is so different from our reality that the idea that we can understand the motivations of the beings that live in that reality, to me, we're in religion anyway. So to me, at that point, go and study religion. That's great. But this isn't science anymore. That's my take on it. And I think the danger of the simulation hypothesis is it kind of sometimes it's just tempting us to confuse science and religion in a way that personally I'm not comfortable with.
Yeah. I mean, I think from my perspective, it's impossible to know, so don't bother. Like, enjoy it as a
Right.
interesting thought experiment, but just don't bother. It's sort of like that same idea of, like, is the universe deterministic or not? Like, who cares? Like, it's not going to affect any decisions that you may choose to make or not. Just get on with life and enjoy mulling it over with your friends at the bar. But beyond that, definitely don't take actions for the way you live your life. Well, Andrew, let's see the book again. So hold up the book. I want people to be able to see the book. There you go. The Universe in a Box.
So yeah, US and UK editions.
I like the one on the right. So which one is the one with the green cube? Which is the one the red?
The green cube. So this is US and Canada.
That's worse.
The UK is
much better.
Well, I let you do the A/B testing.
Yeah.
I couldn't voice an opinion.
Well, there you go. I just did it for you. The red one is vastly better and would jump off the shelf. So congratulations on the book. And I think, it comes at a great time that computers are playing such a powerful role, and to have this partner in helping us understand parts of the universe that are beyond what we can hold in our puny brains at any one time is wonderful. And for me, as a computer scientist, I am just so excited at the potential of this technology being used for good, not to scrape people's computer profiles and learn more about them so they can sell more advertising, but to help us understand the cosmos around us. So thank you, Andrew. You can get even more space news in my weekly email newsletter. I send it out every Friday to more than 60,000 people. I write every word, there are no ads, and it's absolutely free. Subscribe at university.com/newsletter. You can also subscribe to the Universe Today podcast. There you can find an audio version of all of our news, interviews, and Q&As, as well as exclusive content. Subscribe at university.com/podcast or search for Universe Today on Apple Podcasts, Spotify, or wherever you get your podcasts. A huge thanks to everyone who supports us on Patreon and helps us stay independent and keeps ads at a bare minimum. Thanks to all the interplanetary researchers, the interstellar adventurers, and the galaxy wanderers. And a special thanks to Just Paul Davis, Vlad Shipolin, Jay Dennis, David Giltan, Modso, George, Jeremy Mattern, Jordan Young, Tim Whalen, Dave Verabioff, Andrew M. Gross, and Josh Schultz, who support us at the Master of the Universe level. All your support means the universe to us.